Hello, my project is designing of a PI controller for a two-mass resonance system, speed control. The objective of my project is to implement a PI controller that is capable of stabilizing the load speed in reference to a speed signal, and this controller needs to be able to account for motor and load torque disturbances. Designing the PI controller is achieved by using pole placement technique under the identical real part poles assignment criterium. Two mass systems are more common than we think. These can basically describe any two moving or rotating masses that are coupled together with a flexible mechanical shaft. The controls of the control of these systems aims to suppress any shaft torsional vibration, as well as to diminish the effects of the load and torque disturbances. Examples of two-mass systems can be elevators. It can also be robotic arms. Um, it can be rolling mills too. Now the system dynamic equations are presented here. For these dynamic equations, we take the states of the system as the load and motor speed, as well as the shaft torque. Um, these are basically the load and motor speed are always changing, right? Now the inputs that we take for the systems are the motor torque and the load torque, since these will be disturbances for the closed loop operation. Okay, now since this system is analyzed as a linear time invariant, it can also be represented in a state space. By doing so, we can obtain the matrices of the matrices of the system, which can make these calculations much simpler. Okay, the system parameters are presented in here, and these parameters are going to be of very importance later on, as we will need the motor inertia and the load inertia as one of our parameters for selecting the poles. The open loop analysis takes the motor speed as the main equation for this analysis, since measuring the load speed in the open loop is a little bit more complicated. And if we can see that the motor speed is not stable, it would indicate that the load speed is not stable. So in here I present the transfer function of the motor speed. However, for more realistic approach, the viscosities of these systems are not taken into account, since the friction losses are very negligible in real operation, and all the parameters are all the shaft coefficients as are then later represented as frequencies, the anti-resonance frequency and the resonance or natural frequencies. And R, as I mentioned before, is the inertia ratio between the inertia of the load and the inertia on the motor. Here we can observe the open loop results for this system. As we can observe, is not an stable system, and it's also clear from the poles of the system, since two of the poles are in the right-hand plane. So because of this, a PI controller is necessary to be implemented, and here I show the model of the feedback operation, and this accounts for the proportional gain and this for the integral gain. Now, for designing the PI controller, we need to take the transfer function between the load speed and our reference speed signal that is going to be inputted before the torque motor. As we can see, here is obtained. And now we need to compare this equation to the equation that we want our system to behave as. Okay, for doing so, we take into account this equation that follows an ITAE behavior, which yields to a steady state error of 0. For selecting the damping ratio 1, omega 1, omega 2, and damping ratio 2, I use the identical real part method, and these are the equations that govern such criterium. Basically, what we are doing is making that all the poles follow this dashed line, and by doing so, we can assure a stable functioning of the system. Now, using the system parameters, I can obtain the inertia ratio as well as the maximum damping ratio that I could use for my pole selection. Since this is maximum, I select 0.5. And by math calculations from these equations, I can obtain omega 1, omega 2, and later on compare this equation to the equation shown before and find the gain values for the integral and the proportional gains. This will be the transfer function of the system once the gain values are replaced, and these are the poles of the system. As we can see here, all the poles have the same real part value. These are the responses for the load and motor speed that we will look at once again later. For the discrete time control, what I do, I take the integral gain, and I discretize it using the zero order Hall. Since the proportional gain, once discretized, it will be the same value. There is no need to discretize these. Okay, and here we can also observe the results, but I will show that later. And now, for what I wanted was my controller to account for system disturbances. And in here, we can observe that there are disturbances being placed in the motor torque and the load torque. And from the results, we can see that the speed reference is met by the load speed. Okay, so now let's go to the simulation. Okay, perfect. Let's just run it again. Okay, let's first take a look into the open loop. As again, we can see that it's not stable. Here I assign the transfer function for the motor, shaft, and load. These are calculated by the state space representation. Then here is the closed loop for the controller. These are the gains calculated. And let's see the behavior. We can see that it says around 0.14 seconds for the motor speed, and for the load speed it says around 0.12 seconds. Perfect. Here is a discrete time control. As we can see, this is the value that is being discretized. And for the discrete time, we can actually observe that the settling time is lower. It's an average of 40 milliseconds lower between the load speed and in the discrete time and the load speed in the continuous time. Perfect. And now let's see for the disturbances. I believe that let me see something because I was modifying things here. I actually added different value to set the speed control. So this will be the second case that I will show. Let me just run it again. In this case, we are applying the disturbance here in the torque motor. This disturbance take place at 1 second, and for this one plug we are counting a disturbance in the load torque, and it's taking place in 1.5 seconds. So what I want is the load torque to meet my speed signal reference. I was 1 for this case, and after the disturbances I can observe that it sets in 1, but now I want my load speed to set in 2, and that's why I'm adding a new plug, that this plug would represent a more demanding speed. So now the system has to set at 2, which it does, and from here we can see there is the first initial response to the signal speed. There is a disturbance on the load. This is a disturbance on the torque motor. Then we have the signal for a more speed from the load, sorry. And later we have a disturbance in the load that in the case of the elevator, it could be, for example, more people getting into the elevator. Okay, these will be all my presentations. Thank you very much.